All right, so calling all makers of eurorack modules or wannabe makers, I thought I'd start this series in order to take create a tutorial that would take us through the design process of a eurorack module, starting from designing a schematic all the way through to manufacture. So if that interests you, then stay tuned. Here we go. So I'm going to start off just by having a look at the using KiCad to create a schematic diagram for a module. And the module we're going to be working with will be a simple thing, buffered mult, which is used to split an audio signal or a CV signal into multiple outputs so that it can be routed across your rack to other modules. So kind of a simple unit, but something that's really useful for eurorack synthesis. All right, so we're going to start in KiCad and create a new project. And this project I'm just going to call tutorial buffered mult. And I've selected create a folder for it, so I'll create it in a folder with that name. Great. So now we have a tutorial here, and you'll notice that there's a PCB file and a schematic file. So we're going to start in the schematic. So I could either double click that or click over here and it will open up the schematic. Great. So first off, what do we need for just about every single eurorack module? Well, we need some power. So the first thing we're going to do is add some components. So I'm going to press A to add from the symbol libraries. And what do we need to add? Well, we're going to need a connector. So probably Europower has 2 rows of, in this case, 5 odd even mounting pins. So this is what the connector is going to look like. I'm not interested in the mounting pins. I just want, connector generic, 2 by 5, 2 rows of 5 pins, and they should be odd even. So that's going 1, 2, 3, 4, etc. Okay, so let's put that in. I'm just going to put it down here. And now we've got this connector. So what we know from the design spec of the eurorack power is that we have on pin 1, we have minus 12 volts. On pins 3, 5, and 7, we have ground, and on pin 9 we have plus 12 volts. So in fact, just for this, I'm going to flip this vertically on the y-axis. So I just select it or hover over it and press Y, and that flips it. So now the plus 12 is on top and the minus 12 volts is at the bottom. Some modules use plus 5 volt as well, and that's on a 16-pin IDC socket. So we're not using plus 5 volts in this example. We're just using plus and minus 12 volts and ground. So how do we do this? We're going to need to connect both sides, because these pins do exactly the same thing. So for the plus and minus 12 volt pins, and the ground, we're going to want to make a little bit of a trident over here, because all those pins connect to ground. Same on this side. So we're just going to click and create some wires. Great. Let me just make this, make this a little more uniform. Great. So now we want to connect ground. So I'm going to press W creates a wire. Escape gets out of that. So I want to create a wire over here going to ground. Notice it didn't connect. Okay. So, and yeah, so the way we get a power symbol on here is we press P on the keyboard and that gets us to power. And I'm just going to search for ground. Double click and snap that on there. Make sure that it's actually connected. And we can see that it's connected when I drag it around and it moves the wire. Okay, good. Next, we're going to want to create a wire out from here, just all the way to the left. Double click to drop the end of it. And I'm going to duplicate, Command D on Mac, to add a ground over here. So now all of these pins in the middle are connected to ground. And now we need to figure out what to do on the plus and minus 12 volts. So first let's add a plus 12 volts. Press P for power. Plus 12 volts. That looks good. I'm just going to add it about there. And we want to do that again. I'm just going to click again. Minus 12 volts. And to rotate this, because usually negative rails are the other way around, I'm just going to press R until I've got it the orientation how I want it. Always press escape after adding items to get your crosshair cursor back. Right, so now I'm going to connect up a wire that connects us up to plus 12 volts, and let's just get this text out of the way. Maybe just move it down there. Okay. And connect up a wire that connects up our minus 12 volts. So we've got some power rails. Now the problem is we want to make sure that any modules or any components connected to these power rails aren't going to provide reverse feedback into the rest of the modules connected into our rack. So one way to do this would be to insert a barrier diode on both the plus and minus 12 volt rails. So let's press A to add a component. Let's search for a diode footprint. And I know that the common diode that I use actually is a 1N, what is it? Oh, there we go, 1N5817. So that's a 20 volt maximum breakdown, and it's a Schottky barrier diode, rectifier diode that can handle 1 amp. Right, so that should be more than enough for our circuit. So on the plus 12 volt rail, notice how if I drop a component onto a wire, it actually adds it into that wire. So that's kind of cool. So just having to do lots of different traces. So on the 12 volt, note the cathode is pointing away from, it's directional. So the current is flowing this way. So the cathode must be along the line of the current. On minus 12 volt, it's flowing in the opposite direction. So we need to make a duplicate of this and just flip it on the x-axis by pressing X, and we can just place it here. Great. So we've got some reverse current protection on our power rails. Also, what I want to do is add some filtering capacitors. So the one, so again, add A, look for capacitors, and we want, I would just say, we want a polarized capacitor. This means it only works in one direction, so it's got a positive and a negative side, right? So this is where we're going to place a capacitor between the positive 12 volt rail and ground. this is going to act as a reservoir. In other words, if there are slight minor fluctuations in input coming in through these pins, they're going to be flattened out by this. So we get a nice stable signal here. I also need to add a similar one on the minus 12 watt rail. So I'm going to do it like this and just connect it up. All right. Now notice that because, so on a positive rail, we want to connect the positive side of the electrolytic capacitor to the rail and the negative side to ground. And in the case of a minus 12 volt rail, the negative side will be connected to the rail and the positive side to ground. So that's looking good. Just double click on this label here and let's call this a 10 microfarad capacitor. 10 microfarad capacitor. Great. At this point, well, actually, I'll come back as soon as we've got all the power set up. I'll come back and we'll look at how to actually assign the physical footprints that are going to be used on the PCB. But for now, what we also want is a filtering cap or a bypass cap that's going to filter out some high frequency noise on our power lines. So let's add in another capacitor. So press A to add, and let's find just a C capacitor, and we just want there. So that's a non-unpolarized capacitor. The symbol looks like that, doesn't have a plus on it. Right, so I'm going to add this in here and connect it to both rails. And a typical value here is for bypass caps is 100 nanofarads. I can then just duplicate this, Command D, and then move it into place and connect it up to the minus 12 watt rail. Great. One other thing I like to do, just because I do it on pretty much all my modules, is just add a ferrite bead in here just before those bypass caps to filter out any electromagnetic interference. So A again to add, type in ferrite, and ferrite bead small sounds good. Let's double click that, rotate it with R, and just add it in. Duplicate that, put it in place, and add it in. Okay, so of course we've got some text collisions over here, so I'm just going to move these text around a little bit. In fact, we can just move this component. Oopsie. Move this component a little bit. Just drag it along. Drag it along. Y to move it upside down and so on. Okay. Nice. So we've got some power rails, and note this space over here. This we're probably going to use in a little bit to add in bypass caps for some of the integrated circuits or chips, microchips that we're going to add to this board. Okay, so this little piece is going to give us power, and that's quite nice. All right, so over here, of course, what we've got are just symbols on a schematic, and we're ultimately going to want to link this into a PCB. So we've got a nice blank PCB over here. And if I want to link and pull in all the components from the schematic, I would hit this on the PCB, and it's going to give us some problems. Right, so over here it says it cannot add those components that we've added, the ferrite beads, capacitors, and the connection, 10-pin connector, because there aren't any footprints assigned. So we're going to have to assign some footprints before we can add anything into the PCB. So let's go back here. If I double click on one of these polarized capacitors, you'll notice this area for footprint. And currently there's nothing there. So let's see what happens when we click here. We can pull up a list from the footprint chooser of all the different components that are in the library. So over here, I want a capacitor. Now this is capacitor. This is also a time where we're going to have to choose. Are we using surface mount technology, or are we using through-hole technology? So I'm going to be working with surface mount components. And in surface mount, I also know that I want the things not to be so minute that I need a machine to put them together, to solder them onto the board. I want to hand solder stuff. So here you can see this first number is the imperial sizing of the standard components, right? So I know that there's a polarized capacitor over here, CP, electrolytic. Pretty standard sizes are around 4x3, like 4 millimeter size capacitors. So I'm going to choose a 4x3. The 3 is the height, by the way. So 4 mils is across this distance, I guess, over here is 4 millimeters, we can see. So that's what we're talking about. It's the distance between the pin, or the legs, so to speak. So I'm going to double click on that. Oh, just one other thing is when we're inside here, you can have a look and see it might actually have a model associated with it. You can see it's 3 mils high and 4 mils between those legs. Okay, so yes, I'm going to close this up. Oh wow, okay, I'm going to close this because we have our footprint there. I'm going to copy that text, hit OK, double click on the other one, and put the same footprint in there. Great. So now we've got footprints for our electrolytic capacitors. Next, I'm going to add for our ceramic capacitors. And here I'm going to say capacitor SMD. I don't want electrolytics. I want some. These are pretty easy to hand solder. So I'm going to put the 0805s. That's the size again in imperial sizing. So I'm going to double click on that and copy that. Okay. Double click on that, copy it there. Another little trick to understand is that if we want to see all of our components on a kind of a list view, I can go up here and click on this. Click on this here. So now I can see that there are 2 capacitors that have the following footprints. I can, of course, go edit all of this in here as well, right? So this would be another way to edit or to add footprints. This one had a footprint already added, but let's just check if that's what we actually want. Yeah, DO41, this is through-hole technology, so I want to change that to an SMD version. Diode SMD and 0805. Let's go. Of course, I think we want. I think the diodes more often are in 3 to 3 or 1 to 3. Again, if we look at the footprint, just turn that off. Oopsie. We can see that the distance between these points here is somewhere around 2 millimeters, right? So that's what we're looking at there. If I chose 1, 2, 3 and measured again, we're looking at 3.4 millimeters. So let's go with a 1, 2, 3. And this is important when we're actually picking components, right, to solder on here. but I'm going to go with a slightly larger one. In fact, no, I'm going to go with a smaller one, but with a hand soldering option. It's just going to make those pads a little bigger. There's without hand soldering. There's with hand soldering, right? It just makes it a bit neater to work with if you're just soldering directly with a soldering iron. Okay, so that would have allocated that footprint to both of those diodes, right? Same with the ferrite beads. Ferrite bead I'm going to select. Let's just choose an inductor. Hand soldering. That one looks easier to work with, so let's go with that. Okay, so my ferrite beads are now available, and then for the connector, I want an IDC header, and I want it to be a shrouded header, vertical. No, not 2x10, 2x5 would be best. And that looks good. That's the classic eurorack header. Great, so let's choose that. All right, great. So I'm going to do that, and now we should have all of our components. We can double check again. All of them have got a footprint. All right, so I'm going to save that and go back to our PCB. Now when I go to the PCB and I say, and I choose this option to update the PCB from the schematic, it pulls in this dialog. And I'm just going to use all the defaults, update PCB, see nothing happened. I close it, and now attached to my cursor are all those actual components, right? So that's kind of cool. 5x2, we've got, if we look deep in here, we've got ground, 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 and then some J1 pin 10 net and a J1 pin 1 net. Okay, there are our electrolytics, some ferrite beads, very nice, some Schottky diodes, and so on. And if I want to see this in 3D, I can click on this little thing here, and I can press T to show through-hole components, and S to show SMD components. So that's what our module looks like so far. Not super impressive, but hey, it means something about power. Great. All right, so I'm going to close this off because power was the first thing we needed to get in, right? But that's not going to do anything apart from if I had to measure on the board, I could get 12 volts and minus 12 volts. Nice clean rails and a ground between my modular rack and this module. Great. So in fact, what I'm even going to do is I'm going to abstract this power. Yeah, let me do it. I'm going to abstract this power. I'm going to create a sheet, and I'm going to call it the Euro power. So I pressed S, by the way, to create a sheet, and I'm going to call this Euro power. Maybe I should call it plus 12 volts, minus 12 volts, and ground. And let's call the name of the file the same thing. You see what it's going to do? It's going to create another schematic file for this. So I hit OK. Anything else I want to do? No. I'm going to hit OK. And amazing. So there we've got a little block. But what you see on the left here in the schematic hierarchy is it's actually created. So we've got this root page where we're working, and it's created this other sheet, which is all empty, right? And if I double click on that, it takes me to that sheet as well. So what I'm going to do is I'm just going to cut this out of here. I'm going to go to that sheet and I'm going to paste it in over here. So that is our power sheet. So now all we've got in our main sheet is the power. Great. Let me save this. If I go back to my PCB and I refresh, update, there are no changes. It sees no difference. Just that we're separating out sheets and concerns here to keep things simple. All right, so we've got power, but now we want to have some buffered mults. In other words, we need to receive a signal in. It needs to go through a buffer, and then we need to send it out in multiple paths. So I want to have a signal that comes in. I want it to split into 3 buffered signals, and I want to monitor the signal with an LED, so to know how much of a voltage is coming through. So in order to create a buffer, let's start with that. We need an opamp. Now, an operational amplifier, a typical one is a TLO 70X, right? So the TLO 71 is one opamp on a chip. TLO 72 is 2 on a chip, and TLO 74 is 4 of them within a single package, right? So I want how many buffered outputs? I want 3 buffered audio or CV outputs and 1 buffer to control the LED. And the point of buffering is we don't want to affect the input signal by, having it go out to different modules, because that would have the effect of actually changing the signal that's going into all the different modules depending on how they are wired up to use it, right? So, so to create an op-amp, we want to add a component, and I know it's a TLO 74 that I want, so it's got 4 channels effectively on it, and I'm going to say, okay. Now, what we're seeing here is a single op-amp. So you can see there it's unit 1A, TLO 74, right? But there are 4 of them. So when I click here, it drops the first one. Then we've got unit 1B. So I'm going to drop that. Unit 1C, I'm going to drop that. Unit 1D, drop that. And then there's unit 1E, and that's some positive and negative rails that it's looking for, a voltage. So I'm just going to put that over down here. And now we've got, you see my mouse cursor has an op-amp little thingy on it. I want to get rid of that because it's going to start adding more components. So I'm just going to hit escape. And now we have some op-amps. I like, just to keep things a little neater on the diagram, to just move these all into the actual unit that it belongs to. Right. Well, I messed that up a little bit. That's a bit neater. Okay. So now what we have are 4 op-amps, but we want to create a buffer. So there's a very simple way to create a buffer with an op-amp. These are the 2 inputs. There's a non-inverting input and an inverting input. If we send a signal into the non-inverting input and send it to the output as well, so imagine there's a signal coming in here, it's hitting both the non-inverting, and the output at the same time. This will create the effect of duplicating the signal on the output and buffering it. Of course, if we wanted to invert the signal, we would do that the other way around. We would do something like that. That would then, if we send in plus 5 volts in here, we would get minus 5 volts out the other side. Right. In this case, we want to send plus 5 volts and get plus 5 volts out the other side. A perfect replica of this of the input signal. All right. So what I could do now is say, well, let's finish this buffer. So the other pin we're going to put to ground. So I pressed P to get power symbols, typed in ground, and we've got ground. All right, so that's kind of nice. What else do we need? We actually need to represent that there's an input signal coming in here, right? And what I'm going to do, well, let's keep it like this. So where is that input signal coming from? Well, it's probably coming from a jack, right? So I'm going to add an audio jack. I'm thinking, no, it's not going to find it. Let's just look for jack. And I know that I want, so the audio jack's typically used in, here we go, audio jack. I think there's one, a standard one here. It wants, so we want a tip ring sleeve. So it's a mono jack, but it's also got a switch, right? So let's have a look. Audio jack 2 is a tip and a sleeve. So we want actually the same thing plus a switch. Now I don't want both switches. Just the switch on the tip. So yeah, this is the one we want. So I'm going to add in one of those. So there's going to be an input signal coming here. I'm going to turn this upside down, inverted on the y-axis. So press Y. The reason for that is, so the tip is where our signal is coming in, and the sleeve is connected to ground, right? So I could just copy this ground signal over here and put it on there. All right, so that's our input into this buffer, into the buffer. Whoopsie. Make sure it actually connects. And for now, the switch I'm going to ignore. So I'm going to press Q on there to show that we haven't just forgotten it, but we're not using the switch. Great. So, yeah, now the output is going to come out of here and to another jack. Let's flip this on the x-axis by pressing X, and it's going to go to the tip of that jack, and this will be connected to ground. And of course, we want to make sure there's some, just to get the impedance right, we probably want about let's add a resistor. Add resistor, yeah. I prefer this symbol. So I'm going to add this resistor over here and probably make that 1K. Looks pretty good. Great. Now remember, what we're trying to do is we're trying to make, let me just press Q on there. We're not going to implement the switch just yet. So yeah, this looks pretty good. Now, probably what we want to do is also make sure that we're managing impedance of the incoming signal over here. So what I'm going to do with that is, can I just grab this and put a wire in here like so, and grab another resistor and put it here. Let's make this a 1 mega ohm, and connect it up between the tip and ground. See? Make sure it's actually connected. We need to see that junction dot, otherwise it's not actually connected. And I guess we can grab this with G and just move it across like so. All right, so when we hit a supply a signal in here, it will come and get buffered over here and be sent out of this jack. That's pretty cool. All right. Next, of course, we don't just want one output. We want 3 outputs. So I'm going to copy this whole pattern down here. We also wanted an LED, so I'm going to use the last op-amp to buffer the voltage and light an LED over here. But we're going to want to copy this ground to all of those, and we're going to want to copy, see, just these wires. Duplicate. Meh, these are not in alignment, so let me just draw in the wires. It's not that difficult. Okay, and we're going to want to copy this whole thing onto each of those, leaving the space for the LED on the last buffer. Great. So what we've got now is everything is cool. We want to add an LED, add LED, and I want to find a dual bidirectional LED. Now, there's a reason for this. So it's actually got 2 LEDs in one package, right? So what I want to happen is because we often in eurorack we've got signals oscillating between sometimes -10 and plus 10 volts, usually within the range of -5 to +5, or from 0 to +10 volts, right? So so an LED is unipolar. It can only handle a 0 to positive voltage or a 0 to negative voltage, one or the other, but not both. So what we've got here is, if you look at the symbol a bit, 2 LEDs. So imagine we put a positive voltage in here. It's going to be able to flow through this diode, but not through that one. So it will light this LED. If we send a negative signal in here, it's like a pulling. So it's going to pull through that LED and light that one. And that will, if we've got a red and a green LED in one package, then that's going to show us, for example, if we have red in the top, so, that means when we get a negative voltage on here, it's going to light red, and a positive voltage, it's going to light green. So that's kind of cool. It shows us what state, if we've got an LFO or something that's going across positive and minus rails, it'll show us what's happening. Right, so we add an LED in here, and of course, we're going to want to make sure that we don't blow it, we're probably going to want a resistor to ground on the other side. Now this resistor, probably around 300 ohms, I think, is what I used. We can double check these values again against the actual components that we provide, but that should serve us for now. Great. So what we've got is one input, three outputs, buffered, and an LED to show us the state. What we don't have is a working circuit yet because we don't have positive and negative attached rails attached to these op-amps. All right, so this is where we need to do that. So on the top, I'm going to press P for positive, and for power. Type in plus 12 volts and connect that on here. And P again for power, minus 12 volts, and connect that down below. Rotate that and just wire it up. Okay. So this is now should be a completely working circuit. That's quite cool. All right. So save, always save, regular saves. Now, of course, we have the challenge, like we did before, that we probably don't have all the correct packages, footprints associated with these yet. So if I look at the grid, I can see that we've got some blank footprints here. So the LED, I know that it is select your LED. I want a through-hole LED so that we can get it onto the panel, and it's going to be a 3mm package. Nice, with 2 pins. It's just a standard package. It's got a common cathode between the 2 LEDs inside the package, so it's only got 2 pins. So that's kind of cool. All right, so we've got an LED, 3mm LED. These, I want the package now. I have, this is where, so audio connector, there we go. I know that these are, these are the audio connectors. Let's just see if they've got they don't have a model for it, right? So I've created a copy of this in my own library, and I've downloaded a 3D model so you can actually see the jack. So I'm going to use this one. Okay. So I can, well, I don't even need to copy that because, boom, it's on all those audio jacks. Nice. And then the resistors, I want 0805 SMD resistors. So I'm just going to find resistor, SMD, and 0805 hand solder. There we go. Nice, look how tiny that is. And I'm going to have that for all my resistor values. And then the TLO74, it's a 14-pin chip. So I'm going to find over here, I want a SOIC package, which is a SOIC 14 because 14 pins, but I don't want this thing. It's actually a 16-pin package with missing pins. I want just the standard 14-pin package. There we go. So that looks a bit more to the point. So I'm adding that in and apply and save, hit OK. Great. So, all right, so now we've got all the packages there. So if I go back to the PCB, nothing has been added. So I need to synchronize again, update the PCB. I'm going to say update. Oh, I've got some problems. Okay. There's a conflict between the package that I used and this TN pin for those jacks. So let's go and explore what's going on there. So the switch pin, yeah, these. Okay, so we've got a problem. I'm going to go back here and once again, so let's just edit the symbol, press E to edit or just double click it. Right, so I want to change the symbol and I'm going to change all symbols that are that symbol. Well, actually, it's where they match the symbol identifier. And I'm going to find another symbol which has what we want. Now, I believe I have, here we go. I've created a symbol that has the tip and the switch and ground. That's exactly what we want. So I'm going to hit OK. And I'm going to say change it. So boom, it's changed all those symbols, but now, of course, they're not wired up properly. Right, so we can see ground is coming in here and ground is at the top. So I'm going to switch this around again, flip it on the y-axis. And this, so if I did that, ground would now be connected to the switch, and I don't want that exactly. So I'm just going to delete those wires. And our little X over here is going onto the switch. Right, so now the tip of the jack is connected, the switch is not connected to anything, and now that's connected to ground. Great. Let's flip these ones as well. So flip on the Y, flip on the Y, flip on the Y, and grab that, and that, and that. Put them on there. And move this down. Maybe that's the right amount. Maybe it's not. It's not. Okay, everything's connecting up. Let's try moving this down. Let's guess the amount. Hey, we got lucky at that time. Move this down. Guess the amount. Very nice. Okay, so now we've replaced the jacks and the symbols and reconnected them. This symbol has automatically that footprint, and it should have the that footprint has the 3D model associated with it. So I save this, go back to here, and refresh from the schematic. Let's update. Lots more problems. I think I've got a library problem here. Let's just go in here and check the footprint that's on here. That's what I want. Let's go back into the grid and make sure that's on all of those jacks. Wow, it looks surprisingly similar. Oh, it's just the capitalization. Right. Okay, so it's case sensitive, it would seem. Update. Ah, that's looking much happier. Now we can see that the switch is not connected. Our ground is ground and our signal pin is signal. Our tip is signal. Great. So now what we've got this TLO74, we've got a bidirectional LED, and we've got some resistors, and we've got our jacks. Let's see what it looks like in 3D mode. I'm just going to save in 3D mode. Okay, very nice. Looking a little more like what a module, functional module might look like. Okay. But here's the thing. I actually want, because if I laid this out, maybe, if you imagine a module, we could probably have like 2 of these on a single eurorack module. So I want to double up. I want 2 inputs, each input with 3 buffered outs and an indicator. So I'm going to go back to the schematic and think about that quickly. How would we duplicate this? Oh, I've just noticed something. This TLO74, its power rails, we want some bypass capacitors on there. Right, so I'm just going to go into the power and I'm going to copy that capacitor. I'm going to go back to our page here. I'm going to paste it just because it's got the footprint and everything assigned to it already. And I'm going to take the plus 12 in there. I'm going to make another copy over here. Take the minus 12 over here. And I'm going to connect both of these to ground. So let me get a power ground, put it in here, and connect those to ground. Okay, so now we've got proper bypassing on the integrated circuit. Right, I can check. There are no items that don't have a footprint, so that's kind of cool. All right, so if I wanted to duplicate this, I guess quite simply, one approach would be to say, let's take this whole thing and let's duplicate it. And there we go. That was pretty easy. So I've literally duplicated that whole pattern, and now I've got more stuff. So let me go back to the PCB, and if I check the changes, update the PCB, and hey, would you look at that? If I look now in the, great, so I've got 2 rows of jacks and all the exact components to have 2 mults on a single module. That's kind of useful. Okay, so I said that was the one approach. Just going to delete these, save that, and delete all of this. All right, so there's another approach, and that's using sheets like we did down over here. So I could extract the actual buffer portion out of this. Let's think about this. So what I could do is just take all the bits that are control related. In other words, where you're plugging stuff in or out or turning knobs or seeing indicators and so on. Just take all of that stuff and just disconnect it. Okay. So we've got, those are our actual buffers, right? Including this over here. So if I wanted to extract this out and just turn it into a little sub-circuit, basically, what I could do is press S to create another sub-circuit or another sheet. And let's call this quad buffer. Quad buffer. Great. So now I've got this quad buffer sheet. Press escape to get out of that adding sheets mode. And I can just cut all of that stuff. Double click on there and paste it in. And now I've got a sheet that has the quad buffer pattern. And another sheet up here that's just got controls on it. Kind of cool. Now somehow I need to connect these controls into there. So I'm going to go into the quad buffer sheet and make some pins. Let's try a global label. So I'm going to call this input. And I'm going to connect that up. Sometimes we just need to align to grid. Connect that. So that's where the input's coming. And then, of course, there's an output on each of these. So this would be out A. Let's just duplicate this a few times. Let's rename this out B, out C, and out D. Great. So that's our quad buffer, an in and 4 outs. So now, if I go back here and I say place sheet pins, no hierarchical labels found. Well, I was so sure that I had created hierarchical labels. Let's just double check. See. Oh, I pressed global labels. I want hierarchical labels, H. Okay. So we want, well, let's just do input, and it's an input, right? Okay. So let's nuke that one. Yeah, I thought it looked a bit funny. Replace that, and then we press H again, and I quite like the look of this multiple label input. Let's go out A, out B, out C, and out D. Hopefully that's going to do what I want, and we need to change the shape to an output. Okay, so out. Oh, that's beautiful. Let's get rid of those hierarchical labels. There's another reason for those, or another use for hierarchical labels, but let's not worry about that right now. Okay, so now if I go back to the page here and I say place sheet pins, then you see I've got this thing that drags around. So I'm going to take the input over here, let's say. I'm going to have out A, out B, out C, and out D. How about that? And now that block, I can connect the input over there, and I can connect out A, I can connect out B, I can connect out C, and I can connect the LED. So now the beauty of this, I can duplicate this and get another buffer, right, that I can use. And you see what it's done on the end here. It's created, the quad buffer is one we created, and then it's created quad buffer 1. And when I select there, note what's happening with the components when I change pages. It's actually different component references, so a different component, physical component. And if I had to change something in here, like, I don't know, let's just add another 12 volts floating in the middle of space. If I look, it's actually happened across both of those. So it's like two instances of exactly the same thing. Great. So then what I could do is maybe just neaten this up a little bit. That's where the elevator music should be playing. All right, and this one, I just like things to be aligned. So let's just do that. Okay. So now I could just copy this whole pattern, everything except that quad buffer, and make sure at least one of those things connects. Great. Now there's a reason I didn't put all the controls and things in, and we'll see that in a moment. But yeah, okay. Let's save that, go back to the PCB. Let's do a synchronize and hoorah. Yep, it's created all the right components. So if I look again, very nice. Very nice. Okay. Yeah, the reason is I wanted to just have a look because there are these switches here. Theoretically, if this one isn't plugged in, if the second mult hasn't got an input plugged in, we could make it so that it uses so that it takes the signal from that's plugged into the first one and normalizes that into this circuit. So in other words, expanding an input plugged in here would expand out through all of those. So we'd have 6 outputs instead of just 3. So that could be a neat little thing to do as well. And the way, I guess, to do this would be, let's add a label and call this input A. And this is where input A is coming from. Check that that's connected. It is. And we want that input to go into the switch so that, you know, the switch is broken when you the switch contact is broken when you push a jack into this, and then it's going from the jack's tip into the circuit. Otherwise, if there's no jack in here, it's going to get a duplicate of the input from input A and buffer it. So that would be pretty awesome. Quite a neat little change without adding any more components. Okay. So save that, go back over here and update the schematic. So what we should see and what I'm not seeing, oh, there are, I don't know why, yeah, okay, I can see there's a rat's nest there. Good. Maybe it's just, there we go. It wasn't on properly. All right, so now we're at the stage where we have a working circuit. It's got 2 buffered mults that are normalized. The input A is normalized into input B. And we've got power that works. Pretty cool. And those are our 2 quad buffers. Very nice. So the schematic, in theory, should work. The next thing we want to do is actually lay out the board. And for that, I'm going to do this in another video. So thanks for watching. If you made it this far, well done, especially if you managed to follow along and do this for yourself.